Hello again, I'm Bill Wagner.
And I'm James Sturdivant.
And in this module, we're going to start introducing the concept of interfaces, one of the other really key concepts of polymorphism and reuse in object-oriented programming. So as we've been looking at our full roadmap here of all the topics that we're going to discuss, we've talked about encapsulation and inheritance. Now we're up to interfaces, defining contracts that can be implemented by totally different unrelated types. And then we'll move on from there into abstract classes and some of the other techniques like generics to enable reuse. But this module is about how interfaces work in object-oriented programming. What we're going to look at here, we'll define the topic. We'll look at some of the guidelines in terms of what are good practices to work with interfaces. We'll look at some of those practices in some depth. And we'll come back and evaluate some of the results and the risks of different areas. And I think you had a really good comment when we were putting some of the material together about how you name interfaces and how that helps represent what they do.
Yeah, and I think interfaces are a great way to communicate to other developers the intention that you want your class to implement. And so it's that intention that the class is going to be performing. And so we're going to be talking about behavior here. We're not talking about the data. We're talking about the way the class is actually working. And so an interface is a contract that can be implemented by many unrelated classes. And what this means is that the interfaces don't really necessarily contain any of that implementation. They only define what it's supposed to be doing.
Right. So let's look at the actual definition as we work through these concepts and get what is an interface? How are we defining that? You just went through that strict definition. It's a contract that can be implemented by many different unrelated classes. And like I said, it's based on that behavior. This is some property of some action or some set of related actions that some type performs. And when we define an interface, we don't define any of the behavior for any of those methods. We merely define the signatures for any of the properties or methods that are part of any object that implements that interface. Right? And notice we haven't used that is or derives from. We don't derive from an interface. We aren't, a type isn't an interface. It implements it. So the type has to implement the concrete behavior for that particular type. So what does this interface concept give us? Why don't we just use inheritance everywhere? If any of you are familiar with C++, it doesn't have this separation of the concept of deriving from something or implementing an interface. They aren't two separate language concepts. You just derive from a class that may not implement anything. So when we introduce this idea of an interface, first of all, we have a contract definition. It's spelled out that this is not a base class. There's no real behavior here. It's purely a contract.
And I think that's really important with the contract when you're talking about going across boundaries. And so that you have multiple processes and they're maybe not necessarily running inside the same system. And you need to have that contract ability to be able to communicate back and forth on a consistent behavior.
And one of the things that I see in terms of interfaces, and one of the ones that we'll look at is there's an interface in the base class framework called iComparable, which says I can compare two objects to see which is greater or less than. It's used for sorting. And we look at things like, any number implements iComparable. I know which number is bigger. String implements that. The default implementation is alphabetical. But any of our types that we define, we can set an ordering relation to them. And we can say that they're comparable. But the base class framework has no idea how to compare, say, two customers or two teachers or two students. We have to implement that ourselves to say exactly how we want to do that. So it gets us that, but then the base class framework can use that interface and say, because you implement iComparable, code in the base class library knows how to sort those things and arrange them in the order we want. So there's that totally unrelated types that we can work with and be able to treat those similarly because they implement some particular contract. So there's quite a bit of support in the language in C# to bring out interfaces. interfaces are a first-class citizen in all the .NET languages. So they may be public or internal. A private interface doesn't really make sense. It's kind of scoped too narrowly. Interfaces may extend under other interface. So when we go through the code review, we'll look through this in the collection classes, that there are different interfaces that are derived from and extend other interfaces that relate to the collection classes. And any class can implement multiple different interfaces.
Yeah, and that's very different than inheritance
Right.
that we discussed earlier, where you can only inherit from one single base class. With interfaces, you can actually you can implement and use those interfaces across. You can have multiple accounts of them.
Right, and we sort of saw that when we looked at the MVC controller class. It implemented about 8 or 9 interfaces I saw when we were doing the code review. We didn't talk about that then because we hadn't introduced this concept, but that's one of those things that happens is as a type grows, we're going to implement multiple interfaces. Even something as simple as string implements IComparable and IEnumerable and so on. We'll define those, exactly what those do, or you can look them up yourself in the .NET docs. But anytime we do that, a class has to implement every single one of the members of the interface. It's not a, implement this interface but skip some of the members. You have to put them all there. Otherwise you get a compile time error. So when you say you implement something, you have to do it all the way.
Yeah, and that really comes back to that contract component where the classes that are using these interfaces need to know that you've actually implemented that code.
Now, you can make a base class, and we'll get to this in the next module, where you implement an interface or declare that you implement an interface, and you declare some of the methods as abstract and say that, well, this is a base class. Classes that derive from this have to provide a concrete implementation. We'll get into that more in the next module. But for now, understand, if you declare that you implement an interface, you must provide an implementation for that. And you may implement interfaces either implicitly with public, or in the case of internal interfaces, internal members, or you can implement them explicitly, which means those methods are hidden unless your object is being referenced through a reference that's typed to that interface. So in the case where I was mentioning earlier with IComparable, if we look at string, one of the methods for the IComparable interface is called compareTo. If it's implemented implicitly, there's a public compareTo method on string. If they wanted to do it explicitly, you would have to cast string to an IComparable, and then you would see that compareTo method. So there's ways to say that I implement this interface, but it's not part of the public interface of this class. That's often used not quite as commonly. It's pretty rare.
I don't really see that very often.
The only time I see it is when we look ahead and we see generics. There are new improved interfaces with generic types. So the explicit interfaces on some of the classic non-generic interfaces might be implemented explicitly, so they're hidden from some of the newer types. And again, still not really common, but it is one of the techniques we'll occasionally use. In the last module, we talked about this Liskov substitutability principle. See, I can't say it either.
Yeah.
And once again, it's just that we should be able to treat all these things the same. That applies to interfaces. So any type that implements an interface with respect to that interface should be treated just like anything else that implements that interface. So if I can compare strings and put them in order, I can compare numbers, put them in order. I can compare students if we wanted to by grade point. I can put them in order. Whatever it happens to be, if I have that implementation of IComparable, I can treat those types as an IComparable interchangeably in any algorithm. So that has to apply as well. So once again, we don't want to be implementing an interface and then throwing exceptions on some of the methods or doing something totally different in certain areas. We want to try to keep that pretty solid.
Yeah, and I think one of the ways that we potentially make sure that we don't have all of that kind of leaky abstraction, as we called it before, is making sure that that we implement some pretty good guidelines around when we actually create these interfaces. We make sure we follow some simple guidelines. I think one of those ones we've kind of mentioned in the past in the past modules is keeping everything small. And so we want to make sure we keep that contract small. And so that way we don't have that potential of implementing only a partial set of
right. So let's go through some of those guidelines in terms of what kind of things can we do in terms of what makes a good interface representing a good contract. As you mentioned, keeping things small. That we talked about in that encapsulation module and in some of the others, that SRP, single responsibility principle. So it's critically important for interface definitions. Smaller and more focused, right? Notice I mentioned iComparable has this compare to method. It doesn't have methods to test for equality or greater than or equal to, and so on, because they might not be part of that just comparison relationship. Think of our student example for a moment. If I were to compare two students and I want to order them by grade point, two students who have the same grade point, well, they compare the same in ranking, but they're not equal. They're not the same object. Right? They don't refer to the same actual person, as the abstraction. And they're two different objects. They may have different names and so on. But from the ordering relation, they are ranked the same. So by keeping that contract super small and not putting all these other things in, we don't end up with this rule where, well, sometimes when I compare things, just because they compare a certain way, these other things that we think might be true may not actually be true. So the smaller and more focused we create an interface, the better.
Yeah, I think that iComparable is actually only one function itself, isn't it?
And that's relatively common. There are a number of interfaces in the base class library that have exactly one method, or one function or one property. And each interface, in that sense, represents a single feature or a task. Right? When we create an interface, it's for a particular purpose. I want to be able to do something with all objects of a certain type. In iComparable, it's order. In iEnumerable, I want to be able to walk through a sequence. So I want to be able to do that. When we have related things, and we'll walk through this with the collection classes, you might want to consider inheritance of interfaces, making a contract extend another contract. But as we'll even see, that you want to do very carefully, because that starts to get tricky. And it starts to possibly be that leaky abstraction we want to worry about. So keeping those contracts small is definitely a guiding principle. I didn't walk through the entire framework, but I tried to look quite a bit at a lot of the interfaces when we were putting together the areas that we want to look at for code reviews here. I couldn't find interfaces that had more than, say, 5 to 10 different methods in them. I couldn't find an interface that had, 50 methods or 100 methods. That's a lot of work to implement. They were mostly small and focused. And I think that's a very good guideline to follow all the way around. However, you can go too far. There's a technique that will sometimes show up that's called a marker interface. And in a lot of ways, this is something that it kind of can be frowned upon, although there are some successful uses.
Yeah.
So a marker face interface is an interface that has absolutely no methods. So all that we do is check to see that it has and denotes that it implements this interface, and then we can treat it a certain way. But there's no particular actual behavior on that interface or defined methods that say they have to implement. So you could sort of put it on anything. And when we were putting this together, I said, I really don't like those at all. But you had some instances where you said they were useful. So
yeah, in domain-driven design, or DDD, Udi Dahan has created a instance where there is he uses domain events to be able to pass information up and out. We're going to be talking about events a little bit later in our modules, but in that he actually uses the marker interface to be able to explicitly mark a role. And so any event would implement this iDomain event interface. And even though it doesn't implement any logic, it allows them to be able to make sure that not anything can be raised as an event.
Right, and this is one of those, then once you implement that library requires reflection to go find the different things that implement that different event to be able to attach to it. And that's where it can be frowned on in certain ways. In other areas, sure, why not? But let's look at some of the practices. As we build things together, there's certainly practices that will help us come up with better interfaces when we're working on our own domain, and be able to leverage the interfaces that are in the framework more efficiently and more effectively. So first, let's get the idea of a common abstraction for a piece of functionality. So interfaces provide contracts for functionality. So when we think about this, let's look at that idea of enumerating a sequence. So if I have a number of elements and I want to enumerate all of them, they could be anything. I can enumerate a sequence in an array or an array list that we looked at earlier. I can look at some kind of a container element. Maybe I'm writing a WPF app and I want to enumerate all of the child windows of my main window. That's some kind of a container. Think of string. I can enumerate characters in a string, right? I want to get the first character, the next one, and so on. I can look at lines in a text file. I can look at files in a directory. These are all things that I can enumerate in a certain order. I can read bytes from an incoming network packet. That's a very common abstraction. So we want to develop an interface, and base class library has, that allows us to look at anything that allows us to feed sequences at us. And our code will consume that sequence one element at a time. And the storage model, and in fact what's in the sequence, is independent of that abstraction of here's the next item.
Yeah, you definitely see that quite a bit with the characters and lines. So a line in a file is not the same as a list of characters in the string. So that's a great way to show that you can use these interfaces across things that aren't necessarily related.
Right. And then the next big practice that we want to look at is when we're writing libraries often, we want to write libraries and capabilities that work with some code that other developers are going to write to call our algorithms. A good example of this is the base class library containers have sort methods. Well, they can only sort if you tell them, how to define what's greater than or less than for the elements in the collection, because the BCL doesn't know about those. So their contract is, if your code implements this interface, we can sort it. If your code implements some other interfaces, we can serialize it and write it to disk. If your code implements iView result, we can send it to the web as a result. There are different interfaces defined that says if your code implements this, we can treat it as certain things, and you can interact with the framework library in different ways. And I find that's really good for large enterprise applications as well. There's domain knowledge that may be represented in an interface, and then other code can keep extending that and keep growing with that. And that enables us to write these algorithms that can be open for extensions. Once we put some stuff in there, and we have this generic algorithm, and say, if any class that implements this interface can work with this algorithm, right? Find the minimum of something. Any of those are possible.
Yeah, and so another practice that we can start to use interfaces for is for test doubles. And test doubles are a way for us to be able to test the client code that we're working with. And a lot of times we might be able to using an interface, we'll be able to create an instance that doesn't actually touch the database or doesn't actually call out to a service that I'm working with that might be down or it might take a really long time to call. And so we can create these test doubles that allow us to return instances and return the value that we're expecting so that we can test the actual implementation of the details that we're working with.
Right. So we're working with something where if I want to write unit tests, say on one of my MVC controllers, and in order to implement a certain command action, I need to make a whole lot of database calls. I can provide something that wraps my database engine, whether it's Entity Framework or whatever. And if it implements an interface, I can use tools like Mock or just Mock or any of these others to be able to say, act like this thing, and here's what happens when you call it certain ways. And then I can write a lot of unit tests around that don't rely on the contents of a database, which can be kind of brittle over time, or I'm always testing with exactly the same data. Also, I can write things like if I'm writing a distributed system with microservices that run on different machines, I can write interfaces that act like a service running on another machine. And then I can see how my microservice responds if another service isn't available right now, which is hard to test sometimes. especially if what I really want to test is I started working with this other service and then it went down. How do I respond? Right, that can be really hard to recreate in a lab, but with a test double, I can probably make that happen. So it definitely, sometimes those can feel funny because we have this interface that's only implemented by one class, but it is a very important technique for modern software development, I think, to be able to write the kind of unit tests and automated tests that we want and not rely on the entire rest of our entire application all the time. So having looked at some of these concepts in terms of the practices and in terms of what we want to put together, so what do we end up with if we do this well? What kind of things do we see in our app, and what are the risks if we end up, messing it up and creating some really bad interfaces and we get to some of those negative results that we worry about? So the first thing I look for when I'm working with a library where we've added our own interfaces is I really want to see some kind of a natural implementation. So if I create an interface and something is supposed to be able to satisfy that contract, as an idea, as an abstract idea, it should feel pretty natural to put those methods together. The implementation should be obvious, right? I know how compare to should work, right? If I did that one, I know how to enumerate the characters of a string.
Yeah,
the implementation.
You know how to do the equate, like if you're implementing iEquatable, you know how two items are equal to each other.
Right. Yep. And the corollary is the implementations for those interfaces should be complete. I should be able to implement everything on an interface without worrying about, gee, this one doesn't feel like it belongs to this type. That may mean I need to factor out those interfaces a little bit differently. And again, we'll always see that complete implementation of an interface. I don't want to see methods with not implemented exception all over the place because we only implement part of this interface. The rest of it doesn't apply for this type. That may seem like we didn't do a good job. And when I put this slide together, I did say never seeing not implemented exception. That might be too strong. As I'm starting to work, I may have not implemented exception in a few spots, but I really don't want that to live in code for a long time, especially not in a lot of places.
Yeah. So with these interfaces, one of the things that is I guess maybe a potential risk is that because you're not providing any providing that implementation of the code, you might be thinking about copying and pasting some of that implementation, and so you might get some duplication of that code across multiple classes. And so when you do see that, or when you have that inclination to do that, then you want to be maybe reconsidering doing some sort of encapsulation.
Right. So this would be, if we end up with this copied implementation, it might mean our contract is too large. When we need to do a lot of implementation that looks the same in different areas. Things that we can do to fix that is we might produce something like extension methods, which we'll talk about a little bit more later. They're used a lot in LINQ to make very common algorithms based on a core interface. And if we have a lot of convenience methods in an interface, that's a lot of work to do for all the implementers of it. And the term I use is that all-in-one interface, the I do everything interface. Then we have a lot of extra work to try to put those in place. And those give us that copied implementation that feels wrong. And if you have a whole lot of those, it may even indicate inheritance would be better than an interface contract, right? If the shared implementation looks the same in a lot of different disparate types, maybe this is really something where there's inheritance involved in terms of a base class rather than an interface contract. The idea of an interface contract is it should be totally separate implementations of a similar concept with different types. And with that, we will take a short break, and we'll be back and look at some of the examples that we've been talking about in terms of how they're used in the base class library and in your own code. See you soon.